Let's take a moment in this video to look at functions, and we'll start with some review material. A function is an algebraic rule or an algebraic relationship such that each x value corresponds to exactly one y value. The set of all the x values is called the domain, and the set of all the y values is called the range. So here is an example of x's, and each x only belongs to one y. So there are several ways to represent a function. You can represent it as a set of ordered pairs. So here is the set F, made up of the ordered pairs 1, 2, -2, -4, and 3, 6. You can show it as a correspondence or mapping, which is a very good visual way. So let's take our set F and let's map that by taking all of the x's, 1, -2, and 3, and putting those in this oval. And then we'll take all of our y's, 2, -4, and 6, and we'll put them here. And then we map them. 1 belongs to 2, -2 belongs to -4, and 3 maps to 6. So that is called a correspondence or a mapping. We can do it as a table, an x. Now rather than calling it an xy table, I'm going to call it an f of x table. So I have 1 belongs to 2, -2 belongs to -4, and 3 goes to 6. You're used to doing that. We can do it as a graph. If I plot those points, the point 1, 2, the point -2, -1, 2, 3, 4, and then the point 3, 6. If I connected them, this is really small, so I don't really have space to do that. But what you would see is this function happens to be a straight line function. Not all functions are straight line functions. You're going to learn in this course. And then we can also show it as an equation, y equals twice x, or 2 times x. So let's look at identifying a function. It says, example 1, first determine which of the following relations represents a function, and then you're going to give its domain and range. So 1 goes to 1, 3 maps to 9, 2 maps to 4, and 4 maps to 16. Is that a function? Yes, because every x only goes to one y. Its domain is the set of 1, 2, 3, and 4. Its range is the set of 1, 4, 9, and 16. So I just listed my x's and my y's. Looking at the next one, let me pull this down so you can see it. Notice rather than x and y, I have it labeled domain and range. It means the same thing. Is it a function? Well, let's see. 1 goes to 3, 2 goes to 5, 3 goes to 3, 4 goes to 8. Every x only goes to one y, so yes it is. It doesn't matter that this y receives 2 x's. It's where the x's go. Each one only goes one place. The domain is the set 1, 2, 3, and 4. The range is the set 3, 5, and 8. You don't show the 3 twice, even though there are 2 x's going to that y. You only show it once, so there's no repeats in the domain and range. Let's look at this one. Now for me, it's shown as a set. I'm going to map it. It's much easier to see if it's a function when it's mapped. I have -2, -1, 0, 1, and 2 as my x's. My y's are -1, 0, 1, and 2. -2 goes to -1. I'm just going along here. -1 goes to 0, 0 goes to 1, 1 goes to 2, and 2 goes to 2. Is it a function? Yes. Every x only went to one y. And the domain is the set -2, -1, 0, 1, and 2. The range is the set -1, 0, 1, and 2. Let's look at this one. Mapping. I have my x's are -4 and -2. This is repeated. Don't write it twice. My y's are 1 and 0. -4 goes to 1, -2 goes to 1. No problem yet, but now -2 goes to 0. That is a problem. It is not a function. So no, it is not a function because one of our x's went to 2 y's. The domain is -4 and 2, and the range is 1 and 0. Or you can put those in order if you want 0, 1. It doesn't matter. Using the vertical line test, you just drop a vertical line on the graph and you check how many places it crosses. So there, oops, there's a vertical line. It crosses in 2 places, so it is not a function. The domain here, the domain is how far does it go to the left and then how far does it go to the right. And I'm going to be honest with you, this is so tiny, it's very difficult to see, but 1, 2, 3, it looks like it goes from -4 to 4, and then the range -1, 2, 3, 4, 5. It looks like it goes from -6 to +6. I used brackets because it's included. The -6, the +6, the -4, the +4 are included. Is this a function? Check with a vertical line test. It only crosses 1 time, so yes, it is. The domain, you have to think of how far it goes left as it goes up. It goes from -infinity to infinity. The range, the lowest that it goes, though, is right here, -3, and the highest that it goes is infinity. All right, let's look at the next one. Is this a function? Well, if you created an XY chart, every time you put in an X, you're going to get just one Y. This is linear because the X's and Y's aren't squared. So is it a function? Yes, a line is always a function. A linear equation is always a function. So the domain, there's no domain restriction here. I don't have any denominators that contain a variable, and I don't have any variables in an even root radical. So the domain is -infinity to infinity, and so is the range. That is true for all linear functions. Right there, that's true for all. Oops, now, sorry, did you need Dramamine for that? Let's look at this one. I'm going to solve this for y by subtracting an x squared. That gives me y squared equals 1 minus x squared, and now y equals plus or minus, I'm going to take the square root of both sides, 1 minus x squared. So let's think about it. If I do an xy table, if x is 0, that would be plus or minus square root of 1 minus 0. That would be plus or minus 1. So that 0 of x went to 2 different y's. It went to +1 and -1. So is it a function? No. And you don't need to worry here about the domain and the range. We're not going to talk about that right in this instance. So because there is a domain restriction here because I have an x squared under the radical, but don't worry about that on this one. So finding the domain of a function, the domain of a function is the largest set of real numbers that can be substituted in for x. So if we go back to find the domain and the range on these, we've already done those. We can talk about this last one again because it's the only one we didn't do. If you think about what I could put in for x, let's just look at, let me pull this up. Let's just look at what is under the radical. So it's 1 minus x squared. So let's think about this. If I put in x is 0, that would be square root of 1 minus 0. That's okay. If I put in x is 1, it would be square root of 1 minus 1 squared, which is square root of 0. That's okay. If I put in square root of -1, that's going to be 1 minus a -1, which is square root of 2. That's okay. But now what if I put in x is 2? That would be square root of 1 minus 2 squared is 4, which is square root of -3. That can't happen, can it? And in fact, if I take this and I say, at what point would this whole thing be equal to 0? Because that's the lowest it could go. I can figure out exactly what x can be. So if I square both sides, I get 1 minus x squared equals 0, or 1 equals x squared by adding an x squared to both sides. X, if you take the square root, it has to be, remember, greater than 0. has to be greater than 0 or equal to 0. So it has to be, x has to be less than or equal to plus or minus 1. And that's why the domain on that one is very complicated, and we're just not going to worry about that one. All right, looking at our next page, we talk about domain restriction. There are two situations in which there is a restriction, and we've kind of mentioned both of them. One of them is possibly when there is a variable in the denominator, and the other one when there's a variable under a radical sign if it's an even radical. So let's find the domain of each of the following functions by seeing if there's a domain restriction. Well, I don't have a variable in a denominator, and there's no radical, so there's no domain restriction, which means the domain is all numbers, negative infinity to infinity. That didn't come out very well. Let's look at this one. Here I do have a variable in the denominator, so I know that x squared minus 4 cannot be equal to 0. And now I can actually solve that. So x squared cannot be equal to 4. Take the square root. X cannot be equal to plus or minus 2. So the domain restriction is x can't be plus or minus 2. The domain is the set of all x such that x is not equal to plus or minus 2. So that is my domain. Looking at this one, I know that just like I was showing you on that last one, what is under the radical has to be equal to or greater than 0. So I say 4 minus 3t must be greater than or equal to 0. So when I solve that, I can add a 3t to both sides, and I get 4 is greater than or equal to 3t. I divide by 3, turn it around, and I get t must be less than or equal to 4/3. So our domain is the set of all t such that t is less than or equal to 4/3. So it can be a little bit of a problem if you have a variable in the denominator or under an even root radical. So using function notation, when a function is defined by an equation, we use the notation f of x instead of y equals, and we read it f of x. So xy table becomes xf of x table. That's a review. So let's take a function that is defined by f of x equals 2x squared minus 3x, and we're going to evaluate each of these. So I'm going to start with f of x. I'm going to start with my function equals 2x squared minus 3x, and now I want f of 3. Notice I wrote it right underneath it. So that's going to be 2, take out the x, put in the 3, minus 3, take out the x, put in the 3. 3 squared is 9. You do the squaring first. 9 times 2 is 18 minus 9, or f of 3 is equal to 9. Now on this one it says, what is f of x plus f of 3? Well, we just found f of 3, and we already know f of x, so f of x plus f of 3 is equal to f of x, 2x squared minus 3x, plus f of 3, which is 9. So that was actually very, very easy to do. There was nothing to work. This one you need to be careful of. I want 3 times f of x. So that would be 3 times this whole thing. 2x squared minus 3x, or 6x squared minus 9x. So notice that 3 is in the front. Here I want f of negative x. So let's write f of x again first. F of x equals 2x squared minus 3x. F of negative x is 2, take out the x, put in the negative x, minus 3, take out the x, put in the negative x, which is equal to, square that, and it's going to be 2x squared, but a negative 3 times a negative x is a positive 3x. So all I'm doing is replacing this in the x spot in my original function. This says the negative of f of x. So that means if f of x is equal to 2x squared minus 3x, the negative f of x is equal to the negative of all of that, which would be negative 2x squared plus 3x. So that is negative f of x. I forgot a parentheses. This says f of 3x. Please don't confuse that with this one. This was 3 times f of x. Here, I'm going to write my function again. F of x is 2x squared minus 3x. So f of 3x means everywhere there is an x, take it out, put in a 3x. It's just a replacement. So that's going to be 2 square this times 9x squared, 3x times 3x, minus 9x. Or f of 3x is equal to 18x squared minus 9x. And finally, this is our most difficult one. I'm going to pull this up so we've got space to see the whole thing. Let's write our function again. F of x is equal to 2x squared minus 3x. So f of x plus 3 is 2. Take out the x, put in x plus 3, square it. Minus 3, take out the x, put in x plus 3. You have to square this first, and that means FOIL. It does not mean x squared plus 9. So you go over to the side, x plus 3 times x plus 3, you FOIL that out. And you're going to get x squared plus 6x plus 9 before you ever multiply it by 2. Here I can distribute a negative 3. Now I'm going to distribute that 2. So 2x squared plus 12x plus 18 minus 3x minus 9. Or f of x plus 3 is equal to, now we're going to combine like terms. 2x squared, 12x minus 3x, plus 9x, 18 minus 9, plus 9. So you have to be very careful about how you do those. All right, looking at our next page, we have operations on functions. This is new, but it's very, very intuitive. You shouldn't have any trouble with this. This just kind of goes with what you think it's going to be. So it says we can form new functions by adding, subtracting, multiplying, or dividing two functions. So here I have f plus g of x. That's the same thing as f of x plus g of x. So it's intuitive. That makes sense. F minus g of x is f of x minus g of x. F times g of x is f of x times g of x. And here, as you would suspect, f divided by g of x is f of x divided by g of x, as long as g of x does not equal 0 and cause division by 0. So let's try a couple of these. These can get kind of complicated. If f of x is this, g of x is this, h of x is this, and m of x is 2, we want to find the domain of g plus h of x and then evaluate g plus h of 4. Well, in order to find the domain, we first have to find g plus h of x. So g plus h of x is equal to g of x plus h of x. G of x is right here, so it's square root of x. H of x is right here, that's just equal to x. And so that's what it is equal to. Now, I want to know the domain. Well, there's no restriction on this part, but I know that this part, the square root of x, has to be greater than or equal to 0, which would mean that x has to be greater than or equal to 0. So the domain is the set of all x such that x is greater than or equal to 0. So there is my domain. Now we want to evaluate g plus h of 4. So if g plus h of x is equal to this, I'm going to plug the 4 in. So I want g plus h of 4 is going to be g of 4 plus h of 4. G of 4 would be square root of 4 plus h of 4 is just 4. Square root of 4, principal root, is 2. So g plus h of 4 is equal to 6. So there's a lot of places to get lost in that. You really want to watch it. Go carefully. All right, let's find the domain of h minus m of x. Well, h minus m of x is equal to h of x minus m of x. And h of x, if I look up here, is just x minus m of x is just 2. So it's x minus 2. We want the domain of that. There's no domain restriction. So the domain is all real numbers, or negative infinity to infinity. Now I showed this one as an interval. I showed this one in set notation. It doesn't matter which way you do it. I could have done this one as an interval also, 0 to positive infinity. It doesn't matter. Sometimes it's easier to do it one way, sometimes it's easier to do it another. Now we want to evaluate h minus m of negative 3. Well, that's going to be equal to h of negative 3 minus m of negative 3. H of negative 3, go back up here, where is it? H of x is just equal to x, so that's just negative 3. M of negative 3 is 2. It doesn't matter what you're taking, what the x is. It's always going to be 2. So it's just negative 3 minus 2, or h minus m of negative 3 is equal to negative 5. And I think the part that's confusing about this is this. What it's saying is it doesn't matter what your x is. When you take m of it, you always get 2. That's just all it's saying. Okay, let's look at C. It says find the domain of f times h of x and evaluate f times h of negative 1. F times h of x we know is f of x times h of x, and f of x, going back up here, is 3x over 4 minus 2x, and I'm going to multiply that times h of x is just x, or times x over 1, and that's going to give me 3x squared over 4 minus 2x. And now I want to know, what do I get if I plug in a negative 1? I can just go straight here and plug in the negative 1. So that's going to be 3 times negative 1 squared over 4 minus 2 times negative 1, which is 3 over 6, 4 plus 2, because that's a negative 1 there, negative 1, it got kind of messed up, or 1/2. Now we didn't talk about the domain. So the domain of this, is there a restriction? Yes, there is, because there is a denominator. So we know that 4 minus 2x cannot be equal to 0. I'm going to add a 2x to both sides, and I get x cannot be equal to 2. So I know that my domain is the set of all x such that x is not equal to 2. And that's it. All right, we've got one more of those. Let's look at D. We want the domain of g divided by f of x. So I need my other sheet so I can see what each of those functions was. So it's going to be g of x divided by f of x. Well, g of x was square root of x. That's all going to be divided by f of x. And f of x was 3x over 4 minus 2x. So what I really have here is a complex fraction. This one's going to be a little bit harder to simplify. So what I have is square root of x over 1, that's my numerator, divided by 3x over 4 minus 2x. If I do the keep, change, flip thing, I have that that is equal to square root of x over 1 times 4 minus 2x over 3x. So the easiest way to write that is to distribute this, and that's going to give me 4 square roots of x minus 2x square roots of x all over 3x. I can't cross cancel that because this one doesn't have one, so be careful with your cross canceling. Now, is there a domain restriction there? For sure. I know that x can't be 0. That would cause a division by 0, but if I go back to the original right here, this can't be 0 either. So for that to be equal to 0, we already did that one in part C. I know that x also can't equal 2, because if it was a 2, I'd have a 0 here before I ever did keep, change, flip. So you have to go back and look at what you have at the original. So what is my domain? My domain is the set of all x such that x does not equal 0 or 2. So there's my domain. Now let's find g divided by f of 9. So I'm just going to put a 9 in where all my x's are. So I'm going to bring this up. 4 square roots of 9 minus 2 times 9 square root of 9 over 3 times 9. So we're just plugging in that 9. That's going to give me square root of 9 is 3. 4 times 3 minus 18 times 3 over 27, or 12 minus 54 over 27, which is, I'm about to run out of space here, negative 42 over 27. Can that be simplified? Yes, by dividing by 3. And I get negative 14 over 9. So you can see these get can get very, very complicated. This is real important, though, that you didn't just look at what you ended up with to do your domain restriction, but you went back and you looked at what you started with too, because there's a restriction right there before you ever got any further.